Welcome to the MH2801 video segment on the real Fourier series. Now, suppose we're given a periodic function, then we know that it has the following properties. That if f of t plus t, capital T, where capital T is the period of the function, capital T is the period of the function, is equals to its value at f of t. Now, other functions that have this particular property includes cosine 2 pi nt over capital T, as well as sine 2 pi nt over t for n being an integer. Actually positive integers, which are the natural numbers, of course. So we might think that it is possible to expand f of t in terms of the sines and cosines. So it's equals to some n equals to 1 to infinity of, say, an cosine 2 pi nt over capital T plus, again summing from 1 to infinity, of bn sine 2 pi nt over capital T. Now, because cosine at 2 pi nt over t and sine 2 pi nt over t, its average, both average values are 0. For both sets of functions, the average values are 0. We need to add in one more term called a0 to make it possible for f of t to have a non-zero time average. Now, this indeed it is possible. This is indeed possible. This is indeed possible because the sines and cosines form a complete basis over which we can expand a periodic function between 0 and t. Now, this is good. This is good news that we can actually write a periodic function in terms of cosines and sines, but it won't be useful unless we can easily evaluate the coefficients a0, an, as well as bn. Now, a0, in order to evaluate a0, an, and bn, we make use of the orthogonality relations. We make use of the orthogonality relations that we have covered in the previous video segments, and that is, so let me write those down, orthogonality relations. And these are, the integral from 0 to t of cosine 2 pi mt over capital T, cosine 2 pi nt over capital T dt is equals to t over 2 delta mn, and the integral from 0 to t of sine 2 pi mt over capital T, sine 2 pi nt over capital T dt is again equals to t over 2 times the canonical delta. And then finally, the integral from 0 to t of cosine 2 pi mt over capital T, sine 2 pi nt over capital T dt is identically 0. So if we make use of these orthogonality relations between the cosines and the sines, we will be actually able to find the coefficients, the Fourier series coefficients, very easily. Now let me explain what I mean by that. So let me just clear the screen. Write down the expansion again. So ft equals to a0 plus a sum going from n equals to 1 to infinity of an cosine 2 pi nt over capital T plus a sum going from 1 to infinity of bn sine 2 pi nt over capital T. So let us multiply throughout by cosine 2 pi mt over t. Then what we will have is, okay, since we're doing this, we might as well also integrate, okay, from t equals 0 to t equals to capital T. Then what we will get is the integral from 0 to capital T, f of t cosine 2 pi mt over capital T dt. Now this will be equals to the integral from 0 to t of a naught cosine 2 pi mt over capital T dt plus, okay, we move the integration inside the sum, so let's write the sum first. An is a constant, so it doesn't have to be inside the integral. So this is the integral from 0 to t of cosine 2 pi mt over t cosine 2 pi nt over t dt. And then finally we have the bn term, which is integral from 0 to t of cosine 2 pi mt over t times sine 2 pi nt over capital T dt. Now from the orthogonality relation, we know that this term is identically 0. Now this term is also identically 0 because if we integrate cosine 2 pi mt over capital T, it will become sine 2 pi proportional to sine 2 pi mt over capital T. And for the sine function, if you evaluate at capital T and evaluate at 0, it will become 0 at both limits. So therefore this particular integral is 0. Now here we find the integral from 0 to t of cosine 2 pi mt over capital T times cosine 2 pi nt over capital T. Now the orthogonality relation tells us that this is t over 2 delta mn. So let us write that down. This is equals to a sum going from n equals to 1 to n equals to infinity of an times t over 2 delta mn. Now remember, recall that delta mn, the canonical delta, is equals to 1 when m is equals to n and 0 otherwise. Okay, therefore when we sum over n, we find that, let's say n equals to 1, okay, 1 here, but 1 is not the same as m, so this is 0, and therefore we do not pick up any contribution from a1. Now if we put 2 in there, then we can find that it's delta m2. Now if m is not 2, then again this will be 0, and a2 will not contribute. So if we continue summing all the way from 1 to infinity, we find that only one single value of n makes a contribution, and that is when m is equals to n. So only n equals to m makes a contribution. And we see that that is equals to amt over 2. Okay, so what we can then say is that, okay, let me clear the screen and write it nicely again, is that an is equals to 2 divided by t of integral 0 to t ft cosine 2 pi mt over t dt. So this allows us to evaluate one set of coefficients. So when something is wrong here, this is am. Okay, so this is one set of the Fourier coefficients. Now how do we get the other sets? Again, we write down ft equals to a naught plus a sum from 1 to infinity of an cosine 2 pi nt over capital T plus a sum from n equals to 1 to infinity of bn sine 2 pi nt over t. So to get the coefficients bn, what we do is we multiply throughout by sine 2 pi mt over t, and then integrate from t equals 0 to t equals to capital T, and then we will find that it is not difficult to see what we will find. We will find that Bm will be equals to 2 over t times the integral from 0 to t of ft sine 2 pi mt over capital T dt. So this is the other sets of Fourier coefficients. Now what about A0? Now in order to find A0, what we do is we don't multiply by anything. We just integrate ft from t equals 0 to t equals to capital T. Then on the left hand side we have this integral from 0 to t of ft dt, which is actually equals to the time average value of the function f. And this must be equals to, okay, first of all, it is the integral from 0 to t of a naught dt, and then plus, okay, a sum going from n equals to 1 to infinity of an, and then the integral from 0 to t of cosine 2 pi nt over capital T dt, and then also the integral from n equals to 1 to infinity bn, integral from 0 to t of sine 2 pi nt over capital T dt. Now, what simplifications can we make? We find that this is a integral of cosine over one full period. This will be 0. This is the integral of sine over one full period. This will also be 0, even though it is sine and integrates to a cosine. The two cosines cancel because it is cosine of integer multiple of pi times minus the cosine of 0. And of course, we are left with only a naught. And of course, this integral, because a naught is a constant, so it's easy to evaluate this. This is a naught t, which implies that, I'm out of space to write it, but let me just write it on top. Okay, let me write it here. That a naught is equals to 1 over t, the integral from 0 to t of ft dt. So this is simply the time average of the function f of t, and then we are done. We have evaluated. If we evaluate all these integrals, we will have determined our Fourier series for the periodic function f of t.